Start today by reading the question, which we're going to deal with. A colorful lamp is 90 centimeters from a screen. You use a lens with a focal length of 18 centimeters to make a focused image of the lamp on the screen. What are the two possible positions of the lens? Okay, here's the situation. I have a colorful lamp and I have a screen, and they are, in fact, 90 centimeters apart. And I have a lens which has a focal length of 18 centimeters, and I can use this lens to make an image of the lamp on the screen. I'm going to start with a question. If I do this, what type of image am I going to produce? We'll give you some choices. Well, I'm bringing the rays of light from the lamp together to project an image on the screen. And so clearly that's a real image. We have a real image of this lamp on the screen. The question asks us to figure out what are the two possible positions. And think about this. I can put the lens in between the lamp and the screen. And there are possible places where I can put the lens that it will bring the rays of light together to make an image on the screen. What are they? Let's do some calculations. There are two pieces of quantitative information which we're going to take from this passage. First off, the lamp is 90 centimeters from the screen, and the lens has a focal length of 18 centimeters. Before we do any calculations, we want to take a look at the geometry of the situation. Looks like this. Okay, I've got a lamp, that's my object, and I'm just going to draw it as an arrow, as we often do. Then there's a screen that the image is going to be projected on. Then the lens is placed between the object and the screen, okay? And remember how we label distances. The distance from the object to the lens is s, and the distance from the lens to the screen is s prime. Now, we weren't told either of those distances, but we were told that the distance from the lamp, which is the object, to the screen, which is where the image appears, was 90 centimeters. Except we don't want to have that in terms of centimeters. We want to put that in terms of meters, okay? So 90 centimeters, but we're going to rewrite that as 0.9 meters. So that's our basic geometry. Now, our basic thin lens equation, which we'll use to solve for image and object positions, is this. 1 over f, that's 1 over the focal length of the lens, is equal to 1 over s plus 1 over s prime. Now notice something about this particular expression. The roles of s and s prime in the equation are the same as each other. If I were to switch s and s prime, the equation would be exactly the same. So that tells me if I calculate one pair of values for s and s prime, I can use the same values for a second condition. I'll just switch the values of s and s prime, and I'll get a second condition. That's something we can use to check ourselves. But we're going to rewrite this equation. And we can say this. Looking at the geometry of the situation up above, I can say that s, the object distance, plus s prime, the image distance, is equal to 0.9 meters. Given those two pieces of information, we can rewrite the equation this way. 1 over the focal length, but the focal length was 0.18 meters, we were given that, is equal to 1 over s, which is the object distance, plus 1 over s prime. But rather than putting in s prime, I'm going to put in this. S plus s prime is 0.90 meters. So s prime is just equal to 0.90 minus s. So I can rewrite the equation this way. Then with this equation, I can solve it as follows. I'm going to multiply both sides by the following quantities. I'll multiply in turn by 0.18 meters, by s, and by 0.90 minus s. I'll multiply by those three quantities in turn. And when I do that, I get everything from the denominator of the equation into the numerator. And if I do that, what I get is this. On the left, I get s times 0.90 minus s is equal to 0.18 times 0.90 minus s plus 0.18 times s. Next up, I multiply out all the terms of this equation. And if I do that, I get 0.90 times s minus s squared is equal to 0.162 minus 0.18s plus 0.18s. Looking at this equation, two terms that cancel. This term and this term cancel with each other. I'm going to collect terms, bring everything together, And I'll do that in a way that makes s squared positive. But if I collect terms, I get this. S squared minus 0.90 s plus 0.162 is equal to 0. This is a quadratic expression. And I'm looking for roots of the equation. I'm looking for possible values of s. And this is an occasion where I use the quadratic formula. Remember, if I have the following expression, a times x squared plus b times x plus c is equal to 0, the possible roots of the equation are this. The possible values for x are x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. Now the important thing I want to notice in this equation is the following. There's a plus and minus sign here, okay? And that tells me that there's two possible roots of the equation, two possible values for x. So in the equation above, that tells me I'll have two possible values for s, two possible values for s in this equation. And that's good because we know if we get one possible solution for s, there's a second one. We can switch the values of s and s prime. And we were asked to find what are the two possible values for s that work in this equation. So we're ready to put numbers into that equation and solve. And if we do it, here's what we get. We find two possible solutions. The first one is this. S is equal to 0.25 meters, or 25 centimeters. The second one we find is this. S is equal to 0.65 meters, or 65 centimeters. Now for each of these cases, I want to also look at values for s prime. If s is 0.25 meters, or 25 centimeters, s prime is 0.90 meters minus s. So s prime is equal to 0.65 meters, or 65 centimeters. That's my first case. For the second case, s is equal to 0.65 meters, or 65 centimeters. S prime, 0.90 meters, or 90 centimeters, minus s, 0.25 meters, or 25 centimeters. Those are my two possible cases. And here's a great assessment of our results as we go. The two values for s and s prime are just switched. Case 1 to case 2, I switched the values for s and s prime. And that's exactly what we said we needed to do for our two possible solutions. So that gives us confidence in our results. But to give us total confidence in our results, let's look and see how it works in practice. Let's check our answer to see if it makes sense. We found that there were two positions where I could put the lens where I would make an image of the lamp on the screen. We found 25 centimeters and 65 centimeters, and we were solving for s. That's the distance of the lens from the lamp, okay? So our distance from the lamp, 25 centimeters or 65 centimeters. Let's see if it works. To do that, we're going to have to turn out the lights because the image is kind of dim. So we're going to turn the lights down and give it a shot. Now, let's go ahead and see if we get images at those positions. I'm going to take the lens, I'm going to put it in between the lamp and the screen, and you see I got a fuzzy image on the screen, but I need to bring it into focus. I'm going to make the distance from the lens to the lamp bigger, 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 and I reach a point where the image is clearly in focus. If I measure the distance from the lamp to the lens, what I get is 65 centimeters, exactly what we calculated. Now if I measure this distance from the screen to the lens, that distance is 25 centimeters. There's a great symmetry here, because check this out. I'll put the lens back in the middle, and I'll bring it closer to the lamp, and we reach another point where the image is nicely in focus right there. And at this point, the distance from the lens to the lamp is 25 centimeters. And the distance from the lens to the screen is 65 centimeters. It's just the reverse of the two values that I had before. So I have two possible positions. One where the lens is close to the screen and far from the lamp, and one where the lens is far from the screen and close to the lamp. I have those two possible positions where I have a good focus. And in this case, the magnification is less than 1, and in this case, the magnification is greater than 1. But if I move through the whole range of possibilities, you can see there are precisely 1 and 2 places where I get a nice crisp image on the screen. And they are indeed at 25 and 65 centimeters, exactly as we calculated, which is not a surprise. We use the numbers for this very problem, and physics is about the world around us.